Hello, I'm Bill from Great American Classics. Today we're going to talk about something called the Secret WWII Order, the day American artillery became 50 times deadlier. Now, this is one of those stories that doesn't get told as often as it should, even though the people who lived through it and the scientists who made it happen probably changed the course of the entire war. It's a story about real ingenuity, real pressure, and a weapon so secret that for years American commanders were forbidden from using it in certain situations because they were terrified the enemy might figure out how it worked. So let's take a look back and try to understand what they went through and why it mattered so much. The year was 1940, and the world was falling apart. Nazi Germany had already swallowed up most of Western Europe. France had fallen in a matter of weeks, which shocked everyone because France had one of the largest armies in the world, and people assumed they could hold out for years if it came to that. Britain was now alone, facing nightly bombing raids that killed thousands of civilians and threatened to bring the country to its knees. And across the Atlantic, the United States was watching all of this unfold with growing alarm. We weren't in the war yet, not officially, but a lot of people in Washington could see which way things were heading. And one of the biggest problems facing the British, and really anyone trying to defend against air attack, was that shooting down enemy planes was incredibly difficult. It sounds simple enough when you think about it. You've got anti-aircraft guns, you've got enemy bombers coming over. You point the guns at the planes and you fire. But the reality was nothing like that. The reality was that you were trying to hit a fast-moving target that might be flying at 10,000 feet or higher, traveling at speeds of 200 miles per hour or more. And your shells had to travel all that distance and somehow arrive at exactly the right spot at exactly the right moment to do any damage. The mathematics of this problem were brutal. A shell fired from an anti-aircraft gun doesn't travel in a straight line. It arcs upward, slowing down as it goes, affected by wind and air resistance and a dozen other factors. By the time it reaches altitude, the plane it was aimed at has moved hundreds of feet from where it was when you pulled the trigger. And the shells being used at the time had what were called time fuses. This meant that before firing, a crew member had to estimate how long it would take the shell to reach the target's altitude, then manually set a timer on the fuse so the shell would explode at roughly the right moment. If the timing was off by even a fraction of a second, the shell would explode too early or too late, and the plane would fly right through the blast zone without taking any damage at all. The statistics from the early part of the war were frankly depressing. It took, on average, somewhere between 2,000 and 4,000 anti-aircraft shells to bring down a single enemy aircraft. Think about that for a moment. You're a gun crew working through the night, loading and firing shells as fast as you can manage, and, statistically speaking, you might not hit anything at all during an entire raid. The Germans knew this, and the Japanese knew this, and it made them bold. They knew that even heavy anti-aircraft defenses were largely a matter of luck. If you sent enough planes, most of them were coming back. This was the problem that a small group of American scientists were asked to solve in the summer of 1940, and the man who ended up leading the effort was a physicist named Merle Tuve. Now, Tuve wasn't a household name then, and he isn't one now, but he was exactly the kind of person you wanted working on a problem like this. He was brilliant, he was practical, and he didn't have much patience for people who said things couldn't be done. He'd grown up in South Dakota, the son of a Norwegian immigrant, and he'd spent his career at the Carnegie Institution in Washington doing research on the upper atmosphere and on nuclear physics. He wasn't a military man, and he wasn't an engineer in the traditional sense, but he understood how to take a theoretical idea and turn it into something that actually worked. The idea that Tuve and his colleagues were asked to pursue was something called a proximity fuse. The concept was simple enough to explain, even if making it work turned out to be one of the hardest engineering challenges of the entire war. Instead of relying on a timer to detonate the shell, you would build a tiny radio transmitter into the fuse itself. This transmitter would send out radio waves as the shell flew through the air. When those radio waves hit something solid, like the metal skin of an airplane, they would bounce back. A receiver in the fuse would detect those reflected waves, and when the signal got strong enough, meaning the shell was close enough to the target, the fuse would detonate automatically. No guessing about timing, no manual adjustments. The shell would essentially sense when it was near something and blow up at exactly the right moment. On paper, it was elegant. In practice, it was nearly impossible. The challenges were staggering. First, you had to build a radio transmitter and receiver small enough to fit inside an artillery shell. We're talking about a space roughly the size of a coffee cup, and in 1940, radio equipment was not small. A decent radio set might weigh 30 or 40 pounds and take up half a table. Shrinking that down to something that could fit in your hand was going to require completely new approaches to electronics. Second, and this was the part that made experienced engineers shake their heads, the components had to survive being fired from a gun. When an artillery shell is fired, it experiences forces that are almost beyond comprehension. The acceleration is somewhere in the range of 20,000 times the force of gravity. 20,000 Gs. That means every component inside the fuse, every wire, every tube, every connection, would feel like it weighed 20,000 times its normal weight for a fraction of a second. Fragile glass vacuum tubes, which were essential for radio operation in that era, would shatter into dust. Solder joints would crack. Wires would rip free. And remember, all of this had to work perfectly after surviving that kind of punishment. Third, the fuse had to be cheap enough and reliable enough to manufacture by the millions. It wasn't going to do any good to build a handful of perfect laboratory prototypes if you couldn't mass-produce them in factories across the country. Every shell needed one, and the military was firing shells by the shipload. Fourth, and this is something people don't always think about, the fuse had to be safe. You couldn't have it accidentally going off while it was being handled, or while it was sitting in a warehouse, or while it was being loaded into a gun. It had to remain completely inert until it was actually fired, and then it had to arm itself automatically and start working. That's a lot of things that all have to go right, and any one of them going wrong meant the whole project was a failure. Merle Tuve set up shop at Johns Hopkins University in Baltimore, in what became known as the Applied Physics Laboratory, or APL. This was a new kind of organization, a place where academic scientists and practical engineers worked side by side, focused on solving specific military problems as fast as humanly possible. There was no time for the usual academic pace of research. Papers could wait. Publications could wait. What mattered was getting something that worked into the hands of soldiers and sailors who needed it. The work was classified at the highest levels. The Proximity Fuse project was considered just as secret as the atomic bomb project. And in some ways, it was more sensitive, because the fuse was going to be used in combat much sooner. If the enemy figured out how it worked, they could develop countermeasures, or worse, they could copy it and use it against us. So the scientists worked under strict security protocols. And the details of what they were doing were kept from almost everyone outside the project. The first major breakthrough came in figuring out how to make vacuum tubes that could survive being fired from a gun. The solution involved several innovations. The tubes were made much smaller than normal, which helped because smaller objects are generally more resistant to acceleration forces. The internal components were redesigned to be more rugged, with supports and bracing that kept everything in place during the violent acceleration of firing. And perhaps most importantly, the tubes were filled with a special gas mixture and designed so that they could handle the stress without cracking or failing. This work was done by engineers at companies like Sylvania and RCA, working closely with the APL team. It took months of trial and error, testing different designs, firing them from guns, examining the wreckage, and trying again. Slowly, they started to get tubes that could survive. Not every time, but often enough to prove it was possible. The next challenge was the power source. The fuse needed electricity to operate, but you couldn't put a regular battery inside an artillery shell. Batteries of that era were too fragile and too unreliable. The solution was something called a reserve battery, which was essentially a battery that didn't activate until the shell was fired. The design used the spinning motion of the shell in flight to mix the chemicals inside the battery and generate power. When the shell was sitting still, the battery was inert. When it was fired and started spinning through the air, centrifugal force would break a seal inside the battery, allowing the chemicals to combine and produce electricity. It was clever engineering, and it worked remarkably well. By late 1941, the team had prototype fuses that could survive firing, power themselves in flight, transmit and receive radio signals, and detonate when they sensed a nearby target. But prototypes were one thing. Making them work reliably and making millions of them was another challenge entirely. And then, of course, everything changed on December 7, 1941, when Japanese forces attacked Pearl Harbor. Suddenly, the United States was at war, and the need for better anti-aircraft defense became desperate and immediate. The Japanese had demonstrated exactly how vulnerable ships were to air attack. Battleships, carriers, cruisers, all of them could be sunk by determined enemy pilots if the ships couldn't shoot them down first. The pressure on the proximity fuse project intensified enormously. The military wanted the fuse now, not someday, not when it was perfect, but as soon as it could possibly be made to work. Tuve and his team pushed even harder. They were working around the clock, 7 days a week, trying to solve the remaining problems and get fuses into production. The manufacturing challenge was immense. The fuse required miniature electronic components that had never been mass-produced before. Assembly had to be precise, because even small errors could cause failures. And everything had to be done under wartime conditions, with shortages of materials and skilled workers. Dozens of companies were brought into the production effort, including Crossley, Eastman Kodak, Western Electric, and many others. Each company made different components, which were then assembled at central facilities. Quality control was paramount because a fuse that failed at the wrong moment wasn't just a waste of money. It could mean the difference between a ship surviving or going to the bottom with all hands. The first proximity fuses were ready for combat testing by late 1942. The Navy was chosen for the initial deployment, partly because the need was greatest at sea, and partly because there was less risk of the enemy recovering an unexploded fuse and figuring out how it worked. If a fuse-equipped shell missed its target over the ocean, it would fall into the water and sink, taking its secrets with it. The first ship to use the new fuses in combat was the light cruiser USS Helena, operating in the Pacific near Guadalcanal. On January 5, 1943, the Helena was attacked by Japanese aircraft. The gun crews had been equipped with the new VT fuses, as they were officially called, with VT standing for variable time, which was a deliberately vague name chosen to hide what the fuses actually did. When the Japanese planes came in, the Helena's gunners opened fire with their 5-inch guns, and the results were immediate and dramatic. Instead of the usual near misses and wasted shells, planes started falling out of the sky. The fuses were working. The shells were detonating right next to the aircraft, shredding them with shrapnel without needing a direct hit. The Helena's crew shot down several planes in that engagement, a remarkable improvement over what they would have expected with conventional ammunition. Word spread quickly through the Navy, though always in carefully guarded terms because of the secrecy surrounding the fuses. Other ships were equipped with VT ammunition, and the results were consistent. Anti-aircraft fire became dramatically more lethal. One analysis suggested that the proximity fuse made anti-aircraft guns somewhere between 5 and 50 times more effective, depending on the specific conditions. That 50 times figure is where the title of this story comes from, and while the exact improvement varied, there's no question that the fuse represented a revolutionary change in air defense. But the military leadership made a crucial decision at this point, and it's one that shaped how the fuse was used for the next 2 years. They decided that the proximity fuse could be used at sea, where the risk of enemy recovery was low, but it could not be used over land. The fear was that if even one fuse was fired over land and failed to detonate, the enemy might find it, take it apart, and figure out how it worked. The Germans were perfectly capable of copying the technology if they understood it, and they had a massive industrial base that could produce similar fuses in quantity. The thought of German anti-aircraft guns equipped with proximity fuses shooting down American and British bombers over Europe was terrifying. So the order went out: VT fuses for naval use only. No exceptions. This meant that throughout 1943 and most of 1944, American troops fighting on land didn't have access to one of the most powerful weapons in the Allied arsenal. The fuses were there, they were being produced by the millions, but the soldiers in Italy, in France, in the Pacific Islands couldn't use them. It was a calculated risk, trading short-term battlefield advantage for long-term security. And for a long time, it seemed like the right call. The naval results continued to be impressive. The Battle of the Philippine Sea in June 1944, sometimes called the Great Marianas Turkey Shoot, was a lopsided victory for American forces, and the proximity fuse was part of the reason why. Japanese planes flying against the American fleet were cut down in enormous numbers. Over 300 Japanese aircraft were destroyed, many of them by anti-aircraft fire that was far more accurate than anything the Japanese had anticipated. The Imperial Japanese Navy's air power never recovered from that defeat. By this point, the secret was starting to leak out in small ways. Captured Japanese sailors reported that their pilots were terrified of American anti-aircraft fire, which seemed to have become supernaturally accurate. They didn't know about the fuse, but they knew something had changed. German intelligence picked up hints as well, though they never fully understood what was happening. There were rumors of a new American secret weapon, but the details remained elusive. And then came December 1944, and everything changed again. The Germans launched what became known as the Battle of the Bulge, a massive offensive through the Ardennes forest in Belgium that caught the Allied forces almost completely by surprise. German armored divisions punched through the American lines, creating a bulge in the front that gave the battle its name. It was a desperate situation. American units were surrounded, cut off, running low on ammunition and supplies. The weather was terrible, with snow and fog that grounded Allied aircraft and prevented the air superiority that American forces had come to rely on. For a few days, it looked like the Germans might actually succeed in splitting the Allied armies and reaching the vital port of Antwerp. The senior commanders faced an agonizing decision. The proximity fuse had been developed primarily for anti-aircraft use, but by this point, everyone knew it would also work against ground targets. An artillery shell equipped with a VT fuse would detonate in the air above enemy troops, spraying shrapnel downward in a deadly cone. This was far more lethal than a conventional shell, which had to hit the ground and explode upward, giving troops in foxholes and behind cover some protection. Airburst munitions were a known concept, but timing them accurately with mechanical fuses was difficult and unreliable. The proximity fuse made it automatic and precise. The risk of the Germans capturing the technology was real. Shells fired on land would sometimes be duds, failing to detonate, and any dud could potentially be recovered and examined. But the situation in the Ardennes was critical. American soldiers were dying, positions were being overrun, and a German victory could extend the war by months or longer. On December 16, 1944, the same day the German offensive began, the decision was made to authorize the use of proximity fuses for ground combat. The order went out to artillery units across the European theater. Within days, VT-fused shells were being fired at German troops, vehicles, and positions. The effect was devastating. German soldiers had learned over years of combat how to take cover from artillery. They dug foxholes, they used terrain for protection, they spread out to minimize casualties. But cover that worked against conventional ground-burst shells was much less effective against airbursts. The shrapnel came down on top of them, finding them in their foxholes and behind their cover. Casualties in units caught under VT-fused artillery fire were horrific. German soldiers and officers reported that American artillery had suddenly become impossibly deadly. They didn't understand why, but they knew something had fundamentally changed. One German prisoner, an officer, told his captors that a single American artillery barrage had killed or wounded nearly every man in his company, even though they were dug in and properly dispersed. That kind of result was simply unheard of with conventional ammunition. The Battle of the Bulge was eventually won by a combination of factors, including heroic defensive stands by American units, like the 101st Airborne at Bastogne, improving weather that allowed Allied air power to return, and logistical problems that slowed the German advance. But the proximity fuse played a significant role, particularly in the counterattacks that pushed the Germans back. General George Patton, who was not a man given to praising anything that didn't involve tanks, called the proximity fuse the most important development in weapons since radar. Coming from Patton, that was extraordinary praise. The war in Europe was won a few months later, in May 1945. The war in the Pacific continued until August, ending only after the atomic bombs were dropped on Hiroshima and Nagasaki. Both of those events have been analyzed and debated endlessly, as they should be, but the proximity fuse, which arguably had just as much impact on the course of the war, remains relatively unknown outside of military history circles. When historians look back at the technology that won World War II, they usually focus on the big, dramatic things: the atomic bomb, radar, the Enigma code breakers, the long-range bombers, and fighters. The proximity fuse doesn't have the same dramatic profile. It was small. It was hidden inside ordinary-looking artillery shells, and its effects, while devastating, didn't make for the kind of photographs and newsreels that captured public attention. But the numbers tell a different story. Over 22 million proximity fuses were manufactured during the war. They were used in anti-aircraft shells, in artillery shells, in bombs, and eventually in rockets. They saved countless American and Allied lives by shooting down enemy aircraft that would otherwise have killed soldiers and sailors and civilians. They shortened the war in Europe by making American artillery overwhelmingly more effective in ground combat. And they represented a quantum leap in military technology, moving from mechanical systems to electronic ones, pointing the way toward the guided missiles and smart weapons that would come later. The men and women who made this happen deserve to be remembered. Merle Tuve, who led the project with determination and brilliance, never sought fame or credit for his work. He went back to scientific research after the war and continued contributing to physics for the rest of his career. The engineers and technicians at APL, at Crosley, at Sylvania, at all the companies that contributed to production, worked long hours under intense pressure, knowing that what they were building would save lives and help win the war. The factory workers, many of them women, who assembled the delicate components, were doing precision work that was just as important as anything happening on the battlefield. And of course, the soldiers and sailors who actually used the fuses, who loaded the shells and fired the guns, and watched the enemy planes fall out of the sky, they were the ones who put the technology to the test and proved that it worked. There's something worth thinking about in this story, beyond just the military history. It's a story about what people can accomplish when they're faced with a seemingly impossible problem and they refuse to give up. The proximity fuse required solving technical challenges that had never been solved before. It required cooperation between scientists and engineers and military officers and factory workers on a scale that was unprecedented. It required keeping secrets under conditions where a single leak could have cost thousands of lives. And it required making hard decisions, like the choice to restrict the fuse to naval use for so long, that weren't popular but were probably right. We don't always get to know, looking back, whether the decisions made during wartime were the correct ones. History is complicated and full of second-guessing, but in this case, the results speak pretty clearly. The proximity fuse worked. It was kept secret long enough to prevent the enemy from developing countermeasures or copies. And when it was finally deployed in ground combat, it arrived at exactly the moment when it was needed most, helping to stop the last major German offensive and hastening the end of the war. The legacy of the proximity fuse extends far beyond World War II. The techniques developed to miniaturize electronics and make them survive extreme conditions became the foundation for later technologies. The radar-guided and infrared-guided missiles of the Cold War era were direct descendants of the VT fuse, using similar principles of sensing a target and triggering automatically. The electronics industry that grew up after the war, eventually leading to computers and smartphones and everything else we take for granted today, owes a debt to the engineers who figured out how to make tiny, rugged electronic components in the early 1940s. Even the concept of the smart weapon, which can find and hit a specific target with minimal collateral damage, traces its lineage back to the proximity fuse, which was really the first weapon that could sense its environment and make decisions automatically. Of course, there's something sobering about all of this too. The proximity fuse made war more lethal. It killed people, a lot of people, more efficiently than anything that had come before. The German soldiers who died under those airbursts were human beings, many of them conscripts who had little choice about being there. The Japanese pilots who were shot down over the Pacific were young men with families who mourned them. War is terrible, and making the tools of war more effective means making the terrible things happen faster and on a larger scale. I don't think there's an easy answer to that moral complexity. The people who developed the proximity fuse believed, rightly I think, that they were helping to stop a genuinely evil regime that had to be defeated. The Nazis and Imperial Japan were not abstract threats. They were actively committing atrocities that we now recognize as among the worst in human history. Shortening the war by even a few months meant saving lives on all sides, including civilian lives that would have been lost to continued bombing, starvation, and oppression. But it's worth remembering that the same technology that saves lives in one war can take lives in the next. The proximity fuse was a tool, and like all tools, it could be used for good or ill depending on who held it and why. We should be grateful that it was developed by people who were fighting against tyranny and genocide, and we should be thoughtful about how the descendants of that technology are used today. The scientists and engineers who worked on the project understood this complexity better than most. Many of them had mixed feelings about their work, proud of the technical achievement but aware of what it meant in human terms. Merle-Tuve, in particular, was known for his thoughtfulness about the moral dimensions of scientific work. He wasn't naive about the implications, but he also wasn't paralyzed by them. He did what he believed was necessary, and he did it brilliantly. And then he went back to trying to understand the universe through peaceful research. There's something admirable in that, in the ability to face hard choices, make them, and live with the consequences. It's easy to judge from the comfort of decades later, but the people who lived through that time didn't have the luxury of hindsight. They had to make decisions with incomplete information, under enormous pressure, with the lives of millions hanging in the balance. That they made those decisions as well as they did is something we should respect, even as we recognize that no decision in war is entirely clean or without cost. The story of the proximity fuse is also a reminder that wars are not won just by the people who fight them. They're won by scientists in laboratories, by workers in factories, by logistics officers who make sure the right supplies get to the right places, by leaders who make hard strategic choices, by entire societies mobilizing their resources and talents toward a common goal. The soldier who fires the shell gets the credit in the history books, but behind that soldier are thousands of people who made the shell, designed the fuse, loaded it onto a ship, transported it across an ocean, and delivered it to the front. Without all of them, nothing happens. That kind of collective effort is one of the most remarkable things about the American war effort in World War II. We tend to focus on individual heroes, which is natural and appropriate, but the real story is about millions of ordinary people doing their jobs, often in unglamorous and thankless circumstances, contributing to something much larger than themselves. The proximity fuse is a perfect example. Nobody who assembled those fuses in a factory became famous. Nobody who loaded those shells onto ships became a celebrity. But without their work, the fuses wouldn't have existed, and the battles would have gone differently, and the war might have lasted longer and cost more lives. I think there's a lesson in that for our own time, though I hesitate to draw too direct a comparison because every era is different. But the willingness to work toward a common goal, to contribute your skills and labor to something larger than yourself, to trust that what you're doing matters even if you can't see the whole picture, those are virtues that don't become obsolete. The people who developed and manufactured the proximity fuse had those virtues, and we benefit from their work to this day. Let me tell you a bit more about how the fuse actually functioned, because the engineering really was remarkable. When the shell was fired, the enormous acceleration of leaving the gun barrel activated a safety mechanism. This was crucial because you didn't want the fuse to arm itself while it was still near the gun, or the crew firing it. The safety mechanism was designed to wait until the shell had traveled a safe distance from the gun, typically a few hundred yards, before the fuse became active. This was done using a combination of mechanical and electrical switches that responded to the spin and acceleration of the shell in specific ways. Once the fuse was armed and the shell was in flight, the tiny transmitter began sending out radio waves. These waves were at a specific frequency, carefully chosen to be effective at detecting reflections from aircraft-sized targets at useful ranges. The waves spread out in a cone ahead of the shell. And when they hit something solid, like the aluminum skin of a Japanese bomber, some of the energy bounced back toward the shell. The receiver in the fuse was tuned to detect these reflections. But here's the clever part. The receiver wasn't just listening for any reflected signal. It was specifically designed to detect the Doppler shift in the reflected waves. The Doppler effect is the same phenomenon that makes a car horn sound higher-pitched as it approaches and lower-pitched as it moves away. When the shell was approaching a target, the reflected waves would be shifted to a slightly higher frequency than the transmitted waves. The fuse circuitry was designed to detect this specific kind of frequency shift, which helped it distinguish between actual targets and random clutter like clouds or rain. When the signal strength and Doppler shift reached the right combination, indicating that the shell was close enough to a solid target, a firing circuit was triggered. This sent an electrical signal to the detonator, which ignited the shell's explosive charge. The whole process, from detecting the target to detonation, happened in a tiny fraction of a second. The shell might be traveling at 2,000 feet per second or more, so there was no time for complex calculations or decision-making. Everything had to happen almost instantaneously. The engineering tolerances involved were extraordinary, especially for that era. The vacuum tubes had to be precisely manufactured to handle the acceleration and vibration of flight. The battery had to deliver exactly the right voltage at exactly the right moment. The transmitter and receiver had to be perfectly tuned to work together. The detonator had to fire reliably every time, without fail. And all of these components had to be small enough to fit in a space about the size of a can of vegetables, because that's what an artillery fuse is. A metal cylinder may be 4 or 5 inches long and 2 or 3 inches across. The fact that they made millions of these things and that they worked reliably under combat conditions is one of the great engineering achievements of the 20th century. I don't think that's an exaggeration. Compare it to the other major technological developments of the war. Radar was certainly important, but radar systems were large, expensive, and relatively few in number. The atomic bomb was devastating, but only 2 were ever used in combat. The proximity fuse was different. It was deployed by the millions, used in battle after battle, and had a cumulative effect that changed the nature of warfare. The transition from mechanical to electronic weapons started here, in those little cylinders packed with vacuum tubes and wires, flying through the air toward enemy aircraft and troops. The production numbers are staggering when you think about them. Over 22 million fuses were manufactured during the war, as I mentioned earlier. That's a rate of several million per year, which meant factories had to be running around the clock, churning out these delicate electronic devices at a pace that would have seemed impossible before the war started. The quality control problems alone were enormous. Every fuse had to work. Because a fuse that failed meant a shell that missed its target, and enough failed shells could mean the difference between shooting down an enemy plane and being sunk by it. The solution was a combination of rigorous testing and statistical sampling. Not every fuse could be tested, obviously, because testing it meant using it, but samples from each production batch were pulled and subjected to punishing examinations, including being fired from actual guns to see if they survived and functioned properly. If a batch showed too many failures, the whole batch might be rejected, and the production process examined to find the problem. This kind of industrial quality control was still a relatively new concept in the 1940s, and the proximity fuse project helped pioneer techniques that became standard practice in manufacturing after the war. The women who did much of the assembly work in the fuse factories deserve special mention. This was true across the war economy, of course, with women taking on roles in manufacturing that had previously been closed to them. But fuse assembly required particularly fine motor skills and attention to detail. The components were tiny, the tolerances were tight, and the work required steady hands and sharp eyes. Many of the women who did this work had no previous factory experience, but they learned quickly and performed exceptionally. Some of them worked on the project for years without ever knowing exactly what they were making because of the secrecy requirements. They knew it was important. They knew it was helping win the war, but the specifics were classified. Only after the war ended did many of them learn that they had been building one of the most significant weapons of the conflict. There's something poignant about that, I think. These women contributed enormously to the war effort, helped save countless lives, and did so without recognition or even full knowledge of what they were accomplishing. They did their jobs because they needed to be done, because the country needed them, because the men overseas were counting on everyone at home to do their part. That kind of quiet dedication doesn't always make it into the history books, but it's just as important as the more dramatic stories of battlefield heroism. The secrecy surrounding the proximity fuse had some interesting side effects. Because so few people knew about it, there were several instances where American and British forces used the fuses effectively, without fully understanding why they were so effective. Gun crews would be given the new ammunition and told to use it without detailed explanations of how it worked or why it was better than the old type. They just knew that when they fired it, enemy planes started falling out of the sky at much higher rates than before. Some crews developed almost superstitious beliefs about the new ammunition, attributing its effectiveness to various guesses about special explosives or improved propellants. The truth was far more interesting, but they wouldn't learn it until after the war. On the enemy side, the confusion was even more pronounced. The Germans knew, from interrogating prisoners and analyzing intelligence, that American anti-aircraft fire had become more effective. They tried various explanations, including theories about new fire control systems, better trained crews, or improved optical sights. The idea that the shells themselves had been fundamentally redesigned with tiny electronic brains didn't occur to them, partly because it seemed too fantastical, and partly because they had no evidence pointing in that direction. The German military was technically sophisticated and perfectly capable of understanding the concept of a proximity fuse, but they never put the pieces together during the war. By the time VT fuses were being used over land, where duds could potentially be recovered, the war was in its final months and German industry was collapsing under Allied bombing. Even if they had captured a fuse and reverse-engineered it, there wasn't enough time or industrial capacity left to produce copies. The Japanese faced similar confusion. Their pilots reported that American anti-aircraft fire was uncannily accurate, but they attributed this to better gun-laying radar rather than to changes in the ammunition itself. Japanese attempts to analyze captured American equipment focused on radar and fire control systems, which were indeed excellent, but missed the key innovation hiding inside the shells themselves. There's an interesting historical footnote about British involvement in the proximity fuse program. The British had been working on similar concepts before the Americans, and some of their early research was shared when the two countries began coordinating their war efforts. The British contribution included some early ideas about the radio fuse concept and some initial experimental work. However, the massive development and production effort was primarily American, because the United States had the industrial capacity and was not under direct attack in the way that Britain was during the Blitz. British scientists did continue to contribute to the project, and British forces used the fuses extensively, particularly in defending against the German V-1 flying bombs that began hitting London in 1944. The V-1 was an early cruise missile, essentially a small pilotless aircraft carrying a warhead, designed to fly a preset course to a target. They were launched from sites in occupied France and flew across the English Channel toward London and other British cities. Anti-aircraft guns equipped with VT fuses proved highly effective against V-1s, shooting down significant numbers before they could reach their targets. This was one of the first instances of electronic weapons being used against electronic weapons, a sign of what warfare would become in the decades ahead. By the end of the war, the proximity fuse had evolved from a naval anti-aircraft weapon to a multi-purpose technology used in a variety of roles. Artillery fuses for ground combat were just the beginning. Bomb fuses were developed that could detonate at a preset altitude above the ground, creating more effective explosions against troops and equipment. Rocket fuses were created for air-to-air combat, making American fighters more deadly against Japanese and German aircraft. Each new application required modifications to the basic design, but the core concept remained the same: use radio waves to sense the proximity of a target and detonate automatically at the optimal moment. The post-war period saw rapid development of proximity fuse technology, driven primarily by the Cold War and the threat of Soviet bombers carrying nuclear weapons. If enemy aircraft could get through and drop their bombs, the results would be catastrophic in a way that made World War II look mild by comparison. American and British defense planners invested heavily in air defense, and the proximity fuse was at the heart of those systems. The surface-to-air missiles that protected American and European cities from the 1950s onward used sophisticated descendants of the VT fuse, combining radio proximity sensing with radar guidance to create weapons that could hit fast-moving aircraft at long range. The Vietnam War saw extensive use of proximity-fused munitions, including artillery shells and bombs. The technology was mature and reliable by then, and it was deployed in enormous quantities. Some of the controversies surrounding American tactics in that conflict involved the use of airbursts against enemy positions, which caused heavy casualties, but also raised questions about proportionality and civilian protection that continue to be debated today. The Gulf War and subsequent conflicts saw even more sophisticated developments, with precision-guided munitions that combined proximity, fusing with GPS guidance, laser designation, and other technologies. The modern smart bomb, capable of hitting a specific building in a crowded city with minimal damage to surrounding structures, is a direct evolutionary descendant of the VT fuse, even though it uses completely different technology. The fundamental concept of a weapon that can sense its environment and make decisions about when and where to detonate remains the same. Looking back at the original development of the proximity fuse, it's striking how quickly things moved. The basic concept was proposed in 1940. The first prototype was tested in 1941. The first combat use was in January 1943. Mass production was in full swing by 1944. That's an incredibly short timeline for developing and deploying a completely new technology, especially one as complex and demanding as this. It speaks to the urgency of the wartime environment, but also to the talent and dedication of the people involved. They didn't have decades to get it right, they had months, and they did it anyway. The contrast with modern weapons development is striking. Today, new weapons systems often take 10 or 20 years to go from concept to deployment, with cost overruns and delays that would have been unthinkable during World War II. Part of this is because modern weapons are more complex and require more testing to ensure safety and reliability. Part of it is because peacetime bureaucracies operate differently than wartime ones. But part of it is also because we've lost some of the urgency and focus that characterized the war years. The proximity fuse project succeeded because everyone involved understood that failure was not an option, that people were dying every day and would continue to die until the war was won, and that their work directly affected the outcome. That kind of clarity of purpose is rare in peacetime, and maybe it shouldn't be reproduced exactly because the conditions that created it were terrible. But there's something to be learned from how people performed under those conditions, from what becomes possible when talented individuals commit fully to a shared goal. I want to end by talking about the human element of this story, because it's easy to get lost in the technical details and lose sight of what the proximity fuse actually meant for the people affected by it. For the American and Allied personnel who used it, the fuse was a lifesaver in the most literal sense. Gun crews who had spent months firing thousands of rounds without hitting anything suddenly found that their weapons worked. Sailors who had watched helplessly as enemy planes bore down on their ships now had a fighting chance. Soldiers who had huddled in foxholes while enemy aircraft strafed them could look up and see those aircraft falling out of the sky. The psychological impact was enormous. There's a feeling of helplessness that comes from being attacked by an enemy you can't effectively fight back against. The proximity fuse changed that equation, gave American forces a sense of power and competence that translated into better morale and better performance across the board. For the enemy forces on the receiving end, the impact was equally profound, but in the opposite direction. German and Japanese units learned to fear American anti-aircraft fire and artillery in ways they hadn't before. Pilots became reluctant to press home attacks, knowing that the odds had shifted against them. Ground troops developed what military psychologists would later call learned helplessness, a sense that no matter what they did, no matter how well they took cover, the American shells would find them. Morale, which had already been declining as the war turned against the Axis powers, dropped further. The German soldiers who surrendered in the final months of the war often cited artillery as the thing they feared most, and the deadliness of that artillery was, in large part, due to the proximity fuse. For the families and loved ones of the people fighting, the fuse was a hope, even if they didn't know it existed. Every mother worried about her son, every wife feared for her husband, every child wondered if their father would come home. Technologies that made American forces more effective and their enemies less so, technologies that shortened the war and reduced casualties, these were lifelines thrown across the ocean to people who could do nothing but wait and hope. The proximity fuse saved thousands of American lives, maybe tens of thousands, and every one of those lives mattered to someone. That's the human equation that gets lost in discussions of weapons technology, but it's ultimately what matters most. The fuse was not designed out of scientific curiosity or love of engineering. It was designed to protect people and to end a terrible war as quickly as possible. The fact that it worked, that it did what it was designed to do, that it helped bring the fighting to an end and brought soldiers home to their families. That's the real legacy of the proximity fuse. Not the technical specifications or the production numbers or the kill ratios, but the human beings whose lives were preserved because a group of scientists and engineers and factory workers refused to accept the limitations of existing technology. This has been another story from Great American Classics. Before we finish, it's worth taking a moment to remember the men and women who gave so much, and in many cases gave everything, for this country we love. The scientists who worked impossible hours to solve problems that had never been solved before. The factory workers who built millions of intricate devices without ever knowing exactly what they were making. The soldiers and sailors who used those devices in combat, trusting that the people back home had done their jobs. And of course, the ones who didn't come home, who gave their lives on battlefields and beaches and ships at sea, believing that what they were fighting for mattered. Their sacrifice isn't something we should ever forget, and their story still matters today. Thank you for listening.